we're going to try to somehow try to maximize or minimize functions of more than one variable. Actually, the last two sections of this chapter will be dealing with somehow trying to maximize, minimize functions of more than one variable. One where it's constrained optimization. So obviously, finding maximums and minimums are trying to somehow optimize a function. And we'll be doing this both in the unconstrained case and in the constrained case. Somehow where we satisfy maybe some additional conditions, or that they don't necessarily satisfy some additional conditions. So in the first case, or today, we're going to be looking at the unconstrained case. So section 14.7, today is Wednesday. So what that means is the exam number 2 will not be due this coming Monday because we will not be through with all of chapter 14. So I will change the due date until Thursday. So 1 week and 1 day from today. So you'll have some additional time to work on the exam number 2 if you need. Okay, so let's start. Section 14.7, maximum and minimum values. First, let's recall what we did back in Calculus 1. So let's recall extremum. A maximum or minimum is called an extremum. So suppose you have some function, the graph of some function, then these will be maximums, these will be minimums. In this case, this is a local minimum. It is a minimum in the region, but maybe not necessarily a maximum for every value. And these are maximums. This could actually be a local maximum. It's a maximum near it. And this could be a local maximum that's actually a global maximum. It seems to be the largest value for any value of x. It seems to have be here at the highest point. In addition to that, we had things that were called inflection points. These were points that were neither maximums nor minimums, but they kind of looked weird. So they were places where maybe the first derivative was 0, but they weren't a maximum or minimum. I'm going to call it a saddle point, but back when, used to call these actually inflection points. We'll be calling them saddle points, and you'll see why we'll be calling them saddle points in the near future. So notice that for an extrema, we had that the slope of the tangent line was either 0 or it could be undefined. And that having the fact that the slope of a derivative was 0 didn't necessarily mean that it was an extrema. Okay, so f has a local or relative minimum at A if for every x in a deleted neighborhood of A, f of x is always greater than f of A. F has a global, or sometimes called an absolute, minimum if okay, so here, wait 1 second. How am I gonna, if this occurs for all x. Okay, so wait 1 second. Obviously, there must be a page missing here. Okay, so if for all x is greater than f of A. Okay, so that's a global minimum. So f has a local, so f has a local or relative maximum at A if for every x in a deleted neighborhood of A, we have f of x is less than f of A. Next, f has a global or absolute maximum at A if for all x we have f of x is less than f of A. So f of A is the largest value. Okay. So recall we had critical numbers. And so f has a critical number at A in the domain of f if the derivative was equal to 0 at A, or if it did not exist at A. Oops, I wrote it incorrectly. Okay. Okay, so we'll do that. Okay, so let me give you first so really, what does this critical value, or in the future we'll actually call this a singularity, a singular. Okay, so what this really means is that, well, if I tried to somehow invert the derivative, take the reciprocal of the derivative, it wouldn't exist at A. So somehow this has something to do with invertibility, at least locally, of a derivative. And so when we start to look at this in multiple dimensions, this will have something to do with the invertibility of a differential. And well, if I'm looking at a matrix representation of the derivative, then that has something to do with the invertibility of the matrix representation of the derivative, the Jacobian. And so there will be some conditions on the matrix to see if it's invertible, meaning, well, in order for a function to be, for a matrix to be invertible, it has to be a square matrix. And so somehow, if I'm going from Rm to Rn, its rank has to be maximal. So is the rank maximal? And after saying that, is it invertible? Meaning it is the determinant of that square matrix now 0 or not. So let's give you some terminology. So before I can even start to discuss that, let me discuss this matrix representation for the derivative. So if F is a mapping from Rn to Rn, so I'm going to restrict it sort of to an easy, the easier case here, where we have a square matrix where it has, so that I don't have to worry about the maximal rank yet. So then the determinant of the Jacobian matrix, if you recall, the Jacobian matrix, the matrix representation of a differential, is the matrix whose ith, jth entry is partial of f I with respect to xj, let's say at the point A, of f at the point A, the vector A, is the determinant, and we will denote the determinant in this case by just having straight lines of this array, where the entries in this determinant are the entries of your matrix representation of the differential. And this is called, and this is unfortunate, the matrix representation is called the Jacobian. The determinant of the matrix representation is also called the Jacobian. So this is called the Jacobian of f at A, noted by J sub F at A, which unfortunately is also the notation for the matrix representation, Jacobian. So the Jacobian determinant and the Jacobian matrix are denoted by the same notation and are usually called the same thing. So you have to know in the situation if we're talking about the matrix representation or its determinant. And so I will usually say the Jacobian matrix when I mean a matrix. Sometimes I also say Jacobian determinant when I want to say mean that it's the determinant. But please note that outside of this class, when people say Jacobian, you will not know you will not know if they're talking about the matrix or the determinant of the matrix, and that's just sort of life. Okay, so let's do an example. So let me get a little bit here. So let f of xy equal the following. X squared minus y squared, comma, 2xy. Find the Jacobian matrix and the Jacobian. Okay, so let's find J. So this will just be the matrix partial of x1. Maybe I'll write it like this to explicitly show you what it is. Respect to x1. Partial f of x. Let's see, this is ij. I always get mixed up with ij. It's 1, 2, partial of f respect to x, partial of f respect to y, partial of f to respect to y. Okay. Okay, so let's figure this out. So this is equal to okay, so the partial, so x squared minus y squared, that will just be 2x. The partial of xy with respect to x is 2y. Oh, shoot. I did do it wrong. So x's are the same here. Y's are the same there. And so this has got to be a 2 here. Okay. Oh, so this has got to be a 2, and that's a 1. Okay. So I wrote it wrong. That's a 2, and that's a 1. Okay. But doesn't matter. It's going to give me the same thing. Okay, so sorry about that. I was just checking that my notation was correct, and it was not correct. Okay, so this is, and this is F1, this is F2 in this notation. So the partial of this first with respect to x, and then with respect to y, the partial of this with respect to y. Okay, so the partial first with respect to x is 2x with respect to y is minus 2y. The partial with respect to x is 2y. This partial with respect to y is 2x. And that is your Jacobian matrix. Oops. And now let's figure out the determinant. And so my determinant will equal 2x times 2x is 4x squared minus 2y times negative 2y, a negative 4y squared. So 4y squared. And that is your Jacobian determinant. Okay. Good enough. Okay, so recall again from calculus 1 that your extrema occur at critical points or at the endpoints. So you can have either an extrema or you can have an endpoint extrema. And so your interior extrema at some interior critical point, or your extrema can occur at one of the ends. And we'll have to extend this idea to looking at functions more than one variable. And so they'll take us at least till tomorrow, I guess, to be able to do that. So recall, in calculus 1, you really had two differing tests for extrema. The first derivative test and the second, really both depended on looking at Taylor's theorem. So they were really somehow looking at expansions of your function in terms of a power series and going so far down the power series. And of course, if the first or second derivative test didn't work, either you gave up or you'd have to go further in Taylor series to determine the nature of your critical numbers, if you could. Okay, so for determining for determining extrema on a closed set, we had to somehow talk about well, the intermediate value theorem. So let me try to recall the intermediate value theorem. So let me give you some. So a continuous function maps compact sets to compact sets. That's really sort of a characterization of continuous functions. Continuous functions are defined as those functions that take open sets to open sets. A compact set is a set that can be covered by a finite. Suppose you have a covering of your set with a whole bunch of open sets. If you can cover your set with a finite number of these open sets, then you say it's compact. A better way of characterizing compact sets when they're subsets of real numbers is as follows. Compact sets of reals are equivalent to closed and bounded sets. So when I'm saying a compact set, I really just mean, in this case, if I'm just talking about real numbers, a closed set or a closed and bounded set. So a closed but non-infinite set. So this means, I'll restate what I said here about functions continuous functions mapping compact sets to compact sets. That means that continuous functions map closed intervals to closed intervals. An interval meaning a non-finite interval. And so continuous functions map these closed finite intervals to another closed finite interval. So the extreme value theorem says the following. F of x has a local maximum value when x equaling a if there exists a deleted neighborhood of a such that the derivative of f times x minus a is less than 0 for all x in the neighborhood of a, and f of x is continuous at a. Then f of x has a local maximum when x equals a. So this is really the first derivative test. This should have been called the first derivative test. So this is the way that you state this theorem by the name first derivative test. And so oh, I see. That's why. Ah, I see why. This has got to be that a whole. Ah, okay. Well, that's just weird. Okay, so that's why, okay, so this is the extreme value theorem. And that's not. Okay, so one second. Let me delete this for a second. Okay, move this down. That's why it looked a little weird. Okay. Okay. Because that's right there below it is a. Okay, sorry about that. Okay, so this is extreme value theorem right here. Okay. extreme value theorem. Okay, so I said that a continuous function maps closed intervals, closed finite intervals, to closed finite intervals. So let's restate that. And that restatement is called the extreme value theorem. If f is a continuous function on a closed interval, again, I mean a closed finite interval, then f attains both its global maximum and its global minimum value. And these extrema occur at either the endpoints or at an interior critical point. Okay. And so that doesn't quite, okay, so let me make that look a little nicer here. And let's do this. Actually, let's do it in red. Oh, that's a maximum here. And here's the minimum. Aha, okay, so now you can see what I was sort of trying to state, that a continuous function maps this closed interval here to this closed interval here. Okay. So it takes somehow the extrema occur either at the endpoints or at the interior, and it's actually obtained at that interior point. Okay. Okay, so let me, I wonder if that is. Okay. Somehow that was doubled. Okay. Okay, so actually the next logical thing is Taylor's theorem. So we have about 3 minutes. Let me say something about Taylor's theorem. Okay, so the Taylor's theorem and the mean value theorem. So first, the mean value theorem. So the mean value theorem says that if f is continuous and differentiable on the interval x to a, on every value between x and a, then there exists some point I between x and a such that the derivative at psi is equal to the rate of change of f from x to a. So f of x minus f of a over x minus a is just f prime at psi. And so solving for f of x, you get that f of x is equal to f of a minus plus f prime at psi of x minus a. So this looks like the first part of Taylor's theorem, where you just have, well, instead of x, f prime at A is f prime somewhere. And if you kept going, you would have more parts of Taylor's theorem. And so this is just the Taylor's with remainder, where the remainder is, well, you just stop after the first derivative, at the first derivative. And so that's Taylor's theorem. If I subtract f of a from both sides, this is just f of x minus f of a is equal to f prime at psi times x minus a. So now, if I look at f of x minus f of a, well, remember that maximums and minimums were defined as if f of x were greater than f of a, or if f of x was less than f of a. So looking at the sign of the difference, so if I looked up here, I wonder why I doubled it. So if I looked up here, here, the minimum was defined as, well, if f of x is always greater than f of a for all x. So if I subtract the f of a here, it's f of x minus f of a is greater than 0. Gives you a minimum. Whereas f of x minus f of a less than 0 gave you a maximum. If this was true for all x, either in the neighborhood of a or just all x in the case of a actual maximum. Okay, I'm gonna have to get rid of these now. Okay, so this is gonna have to be cleaned up. I don't know how they doubled it. Okay, so now, so really what I want to do here is look at the sign of f of x minus f of a. That will tell me if I'm at a maximum or at a minimum. Yeah, I only have about 2 minutes left. If that. Let me look at the chat. Oh, gotta go. Okay, have to work. Okay, so if I look at the sign of this, that will tell me if I'm at maximum or minimum. Less than 0, maximum. Greater than 0, minimum. So I just have to look at this. The sign of f prime at x minus a is the first derivative test. And eventually, the sign of, supposing that this term were 0, then looking at the sign of this guy, the second term, gives me what's called the second derivative test. You could keep doing that if these derivatives were 0 to give you maybe a third derivative test, fourth derivative test, etc. Okay, so tomorrow I'll have to redo this because I didn't have enough time to really say anything about this. So I'll have to start again talking about Taylor's theorem, the mean value theorem, how that gives you the first and second derivative test, and recall what the first and second derivative test are. So any questions before I leave? Recall that I've extended the due date for the second exam. It will be due 1 week and 1 day from today. If there are no other questions, then I'll see you guys tomorrow. Point 7, maximum and minimum values. So first, let's recall extrema. A maximum or minimum is called extrema. And so each of these are extremum. This is a local maximum, local minimum, a global maximum. And in this case, this is not an extremum, called in this case a inflection point, a minimum. So f has a local or relative minimum at a if for all x in a deleted neighborhood of a, f of x is greater than f of a. In other words, f of x minus f of a is greater than 0. F has a global or absolute minimum at a if for all x is greater than f of a. F of x minus f of a is greater than 0 for all x. Oops. So we're at a local or global minimum. If f at a is, well, if f of x minus f of a is always greater than 0. F of x is always greater than f of a. Maximum. F has a local or relative maximum if for all x in a deleted neighborhood of a, we have that f of x is less than f of a. In other words, oops, I wrote that the wrong way. In other words, that f of x minus f of a is less than 0. F has a global or absolute maximum at a if for all x, we have that f of x is greater than a. So for all x, we have that f of x here is smaller than f of a. Or f of x minus f of a is always greater than 0. A critical number or a singularity. F has a critical number at a in the domain of f if f prime at a is equal to 0 or if f prime at a is not equal to 0. In other words, this has something to do with if the derivative map is singular. And so sometimes we call this a singularity, meaning if the derivative map is not invertible. And if you remember, in order for a matrix to be invertible, you have to have one that it has to be a square matrix, that the determinant can't be 0. And so a condition for a linear map, the derivative, to be invertible is that the rank has to be maximal and the determinant cannot be 0. Okay. Extrema can occur either at interior critical points or at the endpoints. And so let's first look at some tests for extrema at the interior points. And so we have the first derivative test and the second derivative test. Those are probably the two tests that to you in Calculus 1. So let's recall the first derivative test. First, for a local maximum. So to have a local maximum, you look at the place where the first derivative is either 0 or it doesn't exist. And then you look at either side this point. If it goes from increasing to decreasing, then we know that we are at a local maximum. If function is increasing, that means that the first derivative is greater than 0. Function is decreasing, it means the first derivative is less than 0. And so being to the left means that x is less than a, or that x minus a is less than 0. So if I multiply a positive times a negative, I get a negative number. So on the left-hand side, it says that f prime at x minus a is less than 0. And let's look at what happens on the right-hand side. Well, in order for a function to be decreasing, I have to have that the first derivative, is less than 0. And well, if we're on the right-hand side, that x is greater than 0. So that means that x minus a is greater than 0. Again, a positive times a negative is negative. So f prime times x minus a is less than 0. And so notice that we always have here that x prime times x minus a is less than 0. If x prime times x minus a is less than 0 in some deleted neighborhood of a, then we have the first derivative test says that we have a local maximum. And this is really the formulation that will be appropriate for discussion of the first derivative test for multiple variables. So just recall, I'll just say, well, we usually, when we do the first derivative test, we look at the sign of the first derivative and we see, well, it goes from increasing to decreasing, from being positive, the sign going from positive to negative. So restating this again, if as we proceed from left to right, f of x proceeds from increasing to decreasing, then f has a local maximum. Another way of stating this, if there exists a deleted neighborhood of a such that the derivative of f at x exists for all x in the deleted neighborhood of a, then f prime being greater than 0 for x in this deleted neighborhood, and f prime being less than 0 in this deleted neighborhood, and f being continuous with a, implies that f of x has a local maximum at a. If there exists a deleted neighborhood of a such that, so let's reformulate this in the formulation that will be applicable for multiple variables. So if there exists a deleted neighborhood of a such that f prime of x minus a is less than 0 for all x in the deleted neighborhood, and if f of x is continuous at a, then f of x has a local maximum at a. Let's do the same thing for local minimums. So if I have a local minimum, it goes from decreasing to increasing. The first derivative is less than 0 when we're decreasing, and the first derivative is greater than 0 when we're increasing. If x is less than a, then x minus a is less than 0. Negative times negative is positive. If x minus a is greater than, if x is greater than a, then x minus a is greater than 0. And so positive times positive, positive. So we are at a local minimum if f prime at x times x minus a is always greater than 0 in some deleted neighborhood. So our derivative goes from, the sign of the derivative goes from negative to positive. So if, as we proceed from left to right, f of x proceeds from decreasing to increasing, then f of x has a local minimum. If there exists a deleted neighborhood of a such that the derivative exists for all x in the deleted neighborhood of a, then f prime being less than 0 for x in the deleted neighborhood to the left of a, and f prime being greater than 0 for x being in the deleted neighborhood to the right of a, and f being continuous at a, implies that f of x has a local minimum when x is equal to a. Reformulating this into a situation where we can extend this to multiple variables. If there exists a deleted neighborhood of a such that f prime at x times x minus a is always greater than 0 for all x in the deleted neighborhood of a, and if f of x is continuous at a, then f of x has a local minimum when x is equal to a. In addition to the first derivative test, we also have the second derivative test. So in the second derivative test, well, let's look at the local maximum. In order to do a second derivative test, we have to assume that the first derivative at a is 0. So we can only use the second derivative test when the critical number is such that its derivative, the derivative of f at that critical number is 0. We can't use it when the first derivative doesn't exist at this number. So if we're concave down at this point, meaning if we have the second derivative is 0 at a, and actually near a, then we have that we're at a local maximum. So if the second derivative of f at a times x minus a squared is less than 0, of course x minus a squared is positive, so it doesn't change the sign, then we are at a local maximum. This will be, well actually, let's rewrite this as x minus a times f double prime at a times x minus a, that this is less than 0. This will be the formulation that will be more appropriate for talking about functions of more than one variable. Okay, so if f prime at a is 0, and if f double prime at a is less than 0, it's concave down, then f of x has a local maximum at x equal a. We'll also say that that f is negative definite at this point. And so if the first derivative is 0 at a, if f is negative definite, then f has a local maximum at a. If f prime at a is 0 and x minus a times f double prime at a times x minus a is less than 0 for all x not equal to a, well, actually, in some deleted neighborhood of, I should really just say, in some deleted neighborhood of a, then f of x has a local maximum when x is equal to a. Let's look at local minimums. So what does the second derivative test say here? Well, again, if we have a critical number such that f, the derivative of f at that critical number is 0, and such that we are concave up, then we are at a local minimum. So if x minus a times f double prime at a times x minus a is greater than 0, remember the second derivative being greater than 0 says that we're concave up, then this is a condition that we can use to say that our function is has a local minimum at a. So if a has a critical, if f has a critical number at a, and this critical number is such that the first derivative at a is 0, and if f double prime at a is greater than 0, meaning that we are concave up, or meaning that we are positive definite, then f has a local minimum when x is equal to a. The indeterminate case, what will be called degenerate, these will be called degenerate critical numbers. And so the degenerate case. So if f prime at a is 0, and if f double prime at a is 0, then we don't know what happens. The test fails. It could be that we're at a maximum, or it could be that we're at a minimum, or it could be that we are at neither a maximum or a minimum, say a saddle point, an inflection point. So we just don't know what happens. So in order to determine the nature of f of x at x equal a, we might think about using Taylor series. And this might give us an appropriate higher order test. So instead of the first derivative test, maybe it's the fourth derivative test or something. And really, both the first and second derivative test are statements involving the Taylor series. And so it's just statements about the Taylor series, and we're just looking at the Taylor series and saying, well, this is really what happens near there. Okay, so extrema on closed intervals. So this was the interior critical numbers. What about critical numbers on what about extrema on closed intervals? So a continuous function maps open sets to open sets. A continuous function maps compact sets to compact sets. Compact sets of real numbers are equivalent to closed and bounded sets of real numbers. So continuous functions map closed intervals to closed intervals on the real number line. So if I'm talking about the real number line, so continuous functions map closed intervals on the real number line. To closed intervals on the real number line. The extreme value theorem. So the extreme value theorem says that if f is a continuous function on a closed interval, and if then f attains both its global maximum and its global minimum value. These extrema occur at either the endpoints, it's an endpoint extrema, or at an interior critical point. It's one of the interior extrema. So no matter what type of function you have, either the maximum occurs at a endpoint, or well, either extrema occurs at an endpoint or at an interior critical number. So I was talking about Taylor's theorem and the fact that Taylor's gives you the first and second derivative test and higher order test. So let's recall Taylor's theorem. And so Taylor's theorem with remainder, and I'm going to write it in this form for the remainder. So Taylor's theorem and the mean value theorem is really Taylor's theorem. It's just Taylor's theorem where you only go out to the first case. So the mean value theorem, or Taylor's theorem, says that f of x is equal to f of a plus f prime at some psi between x and a times x minus a. In other words, f of x minus f of a is equal to the first derivative at some psi times x minus a. So if I'm looking at the sign of f of x minus f of a, remember this told me if we were at a maximum or at a minimum, then all I have to look at is the sign of f prime at some psi times x minus a. Well, or for every x, I just look at f prime at x times x minus a. Okay. So this will give us the first derivative test. Okay. So if this is always greater than 0, then we'll be at a minimum. And so this just says that, well, all I have to look at is the sign of this guy, formulation for a minimum, for a local minimum in the first derivative test, and being less than 0 for a local maximum. Okay. Next, let's write out the Taylor theorem in this particular case. F of x is equal to f of a plus f prime at a times 1/2 f double prime at psi times x minus a quantity squared for some psi between x. If f prime is 0, then this term goes away. So the sign of f of x minus f of a is just the sign of this, and you don't really need a half. And so the sign of this becomes the sign of this guy. And so if this is greater than 0, then we are at a local minimum. And if it's less than 0, then we're at a local maximum, which is the second derivative test. And so first and second derivative test. So we'll probably want to reformulate Taylor's theorem for the case of functions of multiple variables. So let's look what happens on Banach spaces. The mean value theorem. Let F map A into Y, where A is an open real norm vector space, a real Banach space, X, and Y is a real norm vector space. For each A, X in A, if A contains a line segment from A to X, then there exists some psi between A and X such that the norm of f of x minus f of a is less than or equal to the norm of the differential of f at some psi at x minus a. So this is the mean value theorem. It's the first instance of Taylor's theorem. So Taylor's theorem. Let F map A to Y, where A is an open in the real norm vector space X, and Y is a real norm vector space. And let F be n plus 1 differentiable. So you have F is differentiable, and then you want D of F to be differentiable, and then D, that gives you D squared F. Then you want D, that D squared F is differentiable, that gives you D cubed F, etc. And so if dn of F is differentiable, then we say that F is n plus 1 differentiable. For all x and a in the set A, if A contains the line segment from A to X, then there exists some psi between A and X such that, well, here's the Taylor series. F of X minus a f of A plus the differential of F at A times X minus A plus 1 over 2 factorial the second differential of F at A, F at A evaluated X minus A squared, dot, 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 plus 1 over n factorial, D, the nth differential of F at A evaluated at X minus A to the n. In norm is less than or equal to, well, this error term. 1 over n plus 1 factorial, the n plus first differential of F at A evaluated at X minus A to the n plus 1. Let me give you, so let's figure out what this is saying. So now let me give you the multi-index notation, which simplifies. This is actually a very nice sort of notation. It becomes particularly difficult to write these things in higher dimensions. So things like Taylor series in higher dimensions become quite unyielding unless you have a nice sort of notation. So let alpha be alpha 1, alpha 2, alpha 3, dot, 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 all the way up to alpha sub n, where each of these alphas, I can't see a thing. Each of these alphas, come on. Each of these alphas are whole numbers. Good. The length of A, 1 plus alpha 2 plus alpha 3 plus dot, 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 all the way up to alpha n. And you let alpha thread over whatever operator you're dealing with. And so let's say alpha factorial, because that's what we're going to be using, is, well, alpha 1 factorial times alpha 2 factorial times alpha 3 factorial times dot, 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 alpha n factorial. Let x equal x1, comma, x2, comma, x3, dot, 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 xn. So let this be in Rn. Then x to the alpha is x1 to the power alpha 1 times x2 to the power alpha 2 times x3 to the power alpha 3 times dot, 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 xn to the power alpha n. So now, and let's give this notation. So curly d to the power alpha of f is the length of alpha partial derivative of f with respect to, well, it's the alpha first partial with respect to x1, alpha 2 partial with respect to x2, dot, 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 the alpha n partial with respect to xn. So now let me formulate this a little nicer. When I kept saying that, you know, if you had something, some point inside your set, and another point inside your, joining those points, then there was some point along that line, psi, that gave us this. So let me tell you, well, what are sets that contain all line segments? And so a set is convex if it contains every line segment joining any points in the set. So this is an example of a set that's not convex. So if I take a point, 2 points in the set, if I can find 2 points in a set such that not every point along the line segment is completely contained within the set, then this set is not convex. So since there are some points here that are not in the set, then this is not a convex set. So you can think of a convex set like, you know, a ball is a convex set, a square, a soccer ball. Those things are convex sets. But this is not this is concave, it's not a convex set. Okay, so now that I've given you some terminology, I can now formulate a Taylor's theorem for a function going from Rn to R. Then it won't look so bad. And so we can actually do these calculations relatively nicely. Okay, so suppose f is a function from Rn to R. And suppose that f is ck plus 1, meaning that every derivative up to k plus 1 are all exist and are all continuous. So suppose that if you look at every derivative up to k plus 1, each of the derivatives exist and they are at every point in the set S, and they are continuous. So that gives us a lot of, that makes everything really nice. We had all those degenerate cases when the function was not ck plus 1. So on a open convex set S, if A is an S and A plus H is an S, then, and of course these are I didn't want to put little arrows here because it didn't look so nice, because I'm now using the multinomial notation. So I'm not going to put little arrows above these. Just know that these are n-dimensional. So this is n-dimensional, and so is this h. Is an S, and a plus h is an S. Then f evaluated a plus h is the sum of the length of each of these alphas less than or equal to k. So you're going to sum this multi-index such that if you add up all the values in this multi-index, they're less than this value k up here. Well, remember that this was the multinomial notation for the multi-index alpha derivative. So this is the partial to the multi-index alpha of f evaluate a divided by alpha factorial. Again, this is a multi-index factorial times h to the alpha. Remember, again, this is a multi-index. So this is it has some components, h1, h2, to hn, and this is alpha 1 up to alpha n. And so it's, h1 to alpha 1, h2 to alpha 2, blah, blah, blah. Okay, plus a remainder term. So plus an error. So plus r of a comma k h, where the remainder is given. Well, you can do it in Lagrange's form, which is what we did above. So this error term, r sub a comma k at h, is a sum that the length of this multi-index alpha is equal to k plus 1. The partial to the multi-index alpha of f that's wrong, at a plus ch. A has n components, and so does h. C here is just a scalar, all divided by the multi-index alpha factorial, h to the multi-index alpha, for some c between 0 and 1. Okay. And in integral form, the remainder looks as follows. The remainder r sub a comma k at h is, and you have that one, k plus 1 sum, because you got to get rid of that guy, k plus 1, so the sum alpha, the multi-index alpha, is equal to k plus 1, h to the alpha, the multi-index alpha, over the alpha factorial for the multi-index alpha, integral from 0 to 1, t minus 1 minus t to the k times the partial to the multi-index alpha of f at a plus th. Oh, good, I put the a correct here. And you're integrating with respect to t. Okay, so notice, again, if you only write out the first of these, this is going to be some partial to the first. So the first partials times h to, alpha, which is going to be to the first. And so we want these to be greater than 0, give a local minimum, and less than 0 to give a local maximum. Okay, so if you notice, it's in the same, except we called it a C, an H instead of a C, but it's in the same formulation as above. So first derivative test, first for a local minimum. Let A be in the domain of F. Let U be in some vector space V, and let U be a unit vector. Of course, this is a norm vector space. It's probably it's a Banach space, let's say. F of A plus HU. Let this be right continuous at H equals 0. And let F of A plus HU be right differentiable H equals 0. Let the directional derivative in the direction of U of F of A plus HU be greater than 0 for all sufficiently small h greater than 0. Then F has a local minimum at A. Let's reformulate this. And this will be sort of the easiest sort of case to look at when we're doing problems. Let F be continuous at A. Let the gradient of F exist on some deleted neighborhood of A. Then, if nabla F at X dot X minus A is greater than 0 for all X in a deleted neighborhood of A, then minimum at A. Let's look at a local maximum. Let A be in the domain of F. Let U be a unit vector in the norm vector space V. Let F at A plus HU be right continuous at H equals 0. Let F of A plus HU be right differentiable at H equals 0. Let the directional derivative in the direction of U of F of A plus HU be less than 0 for all sufficiently small h greater than 0. Then F has a local maximum at A. Again, let's reformulate this. So it'll be easier to actually implement this. Let F be continuous at A, and let del F exist on a deleted neighborhood of A. Then the gradient of F at X dot X minus A being less than 0 for all X in the deleted neighborhood of F of A implies that F has a local maximum at A. Okay, so these are some extra things that we added. Jacobian matrix. So let F be a mapping from an open subset of Rn to Rm, and suppose that F is differentiable at A, then the matrix representation of the differential of F at A is called the Jacobian matrix of F at A. It is given by this notation. The jth entry is just the partial of F sub I with respect to X sub J. The Jacobian is just the determinant of this Jacobian matrix. So if F is a mapping from Rn to Rn, then the determinant of the Jacobian matrix, this matrix above, the matrix with component, whose jth component is the partial of the F sub I with respect to X sub J at A, this Jacobian of F at A, this is the Jacobian of F at A, then the determinant of this Jacobian matrix, the determinant of this, is called the Jacobian of f at A, and is denoted by J sub f at A. So let f of x, y equal x squared minus y squared, comma, 2xy. Then we want to find the Jacobian matrix and the Jacobian. In respect to x, partial of x squared minus y squared is just 2x. Partial of f1 with respect to y, the partial of x squared minus y squared with respect to y is minus 2y. The partial of f2 with respect to x, the partial of 2xy with respect to x is 2y. The partial of f sub 2 with respect to y, the partial of 2xy with respect to y is 2x. Therefore, the Jacobian matrix is the matrix with entries 2x minus 2y, 2y, 2x. The Jacobian is just the determinant of this Jacobian matrix. So it's just 2x times 2x, 4x squared, minus 2y times minus 2y, subtracting negative 4y squared plus 4y squared. Now, I had the Taylor's theorem, and the second term, so the first term was just f of a, the second term was the differential of f at a times some x minus a. The next term was plus 1/2 some second derivative of f times x minus a quantity squared. So we can think of this as some sort of term involving, well, if I look at the matrix representation, it'll be some matrix times x minus a times another x minus a term. So let's first look at what that will look like, because I want to somehow determine, see if I can find the sign of objects of that type. Because if the first derivative was 0, then the f of x minus f of a, the sign of that is just the same as the sign of that second term or third term in Taylor's theorem. The 1/2, don't worry about the 1/2 factorial. So the 1/2, well, 1 over 2 factorial, which is 1/2, don't need to worry about that, doesn't give us anything about sign, times the this matrix representation of the second derivative, and we'll give that eventually a name, times the x minus a squared. And somehow you've got to, well, in the multi-index notation, we were able to make sense of what that meant. Okay, so let's look at quadratic forms. That will tell us how to study objects of this type. For those people who took linear algebra, a lot of this stuff is actually linear algebra. The quadratic form. So let us study when equations of the form, and I'll just look at equations looking like this: ax squared plus 2b xy plus cy squared. When these are either always positive, when these when I'll be able to tell the sign of things of this form for every x and y. So what conditions do I need on A, B, and C so that things of this type will always have a particular sign? Okay. By the way, I didn't need a 2b here. I could have made it more general, but it's easier just to study this type because it'll be easier for the algebra. It'll be easier to study. Okay, so in other words, for people knowing symmetric forms, I don't really have to look at the symmetric case of these quadratic forms. I could look at the regular case and then just make it symmetric. Okay, so let's recall that if I make this, actually, let me write this way. So it looks like ax squared plus 2by x plus cy squared. So this is quadratic in x. And so, well, if I have something quadratic in x, I can tell if it's always going to be positive or negative. Well, it'll always have a sign. It will change sign if it crosses the x-axis. So if I have that my quadratic, my parabola, somehow crosses the x-axis or touches the x-axis, then it will, well, if it crosses the x-axis, it'll change sign. So if I have that, it's either always above the x-axis or always below the x-axis, then it'll always be of one sign. So, let's recall that if I look at my discriminant will tell me what type of roots I have. If the discriminant, and let's assume that all of these things, A, B's, and C's are all real. So if I have some real quadratic, and if I look at my discriminant, if my discriminant was equal to 0, then I have one double root. If my discriminant was greater than 0, then I have two unequal real roots. I don't want those. If I have that, the discriminant is less than 0, then I have two unequal non-real roots, which means I don't have any place, I don't have any roots, any real roots, meaning that I never cross the x-axis, meaning that it's always either positive or always negative. And so recall that a quadratic expression will have a constant sign, i.e. will not cross the x-axis, i.e. does not have a real root when the discriminant is negative, because then you'd be taking the square root of a negative number. And so let's look at my discriminant. My discriminant is b squared minus 4ac. So in this case, the coefficient of x is 2by. The coefficient of x squared is a. The coefficient, the constant term, is cy squared. So I want that the discriminant is less than 0. And so 2 squared is 4, b squared y squared minus, well, 4ac y squared. I can factor out a 4y squared. So this becomes 4y squared times b squared minus ac is less than 0. So, well, this is positive. So the only way that this can be negative is if b squared minus ac is less than 0. Let me write it in the following way. So this will always have the same sign so long as ac minus b squared is greater than 0. Note that if I have the following matrix multiplication, the matrix, the vector, with components x, y, times the vector a, b, b, c, times the vector x, y. Well, let's multiply these vectors together. So do the dot product here of this row vector and this column vector. So it's ax plus by. Let's do the dot product between this row vector and this column vector, bx plus cy. And now let's do the dot product between these two vectors. So it's ax plus by times quantity times x. So it's ax squared plus bxy. And then it's the quantity bx plus cy, quantity times y. So bxy plus cy squared. Let's add these together. Oh, and so if I add these guys together, I just get ax squared plus 2bxy plus cy squared, the thing that I was studying. So this will always have the same sign, so long as ac minus b squared is greater than 0. So long as if I multiply this way, oh, that is b squared. Ah, okay. So long as its determinant is greater than 0. And so if I write the following, say, and let's just call it x1, x2, and instead of calling x and y, I called it x1 and x2, and instead of calling a, b, and c, I call a the second partial of f with respect to x, the mixed partials here, and the second derivative, second partial of f with respect to y. Then this quadratic form will be either greater than 0 or less than 0 for all values of x1 and x2, so long as this determinant, the second partial of f with respect to x, times the second partial of f with respect to y, minus the product of these mixed partials, is greater than 0. By the way, in my formulation, I assumed that the mixed partials were equal. You don't really need to assume the mixed partials are equal. It just makes the algebra easier. So usually we give it where we just say that these mixed partials are equal. So let me give you some terminology. Definite forms, semi-definite forms. Okay, so a quadratic form, q of x, which is something of the form that we've done above. I just wrote it as, well, suppose we have vectors written as columns. And I have some square matrix, is, well, the length of these vectors. So the transpose of x times a times the matrix A times x. So this is x here, and this is the transpose of x, written when you write it the other direction, is positive definite if this is greater than 0 for all non-zero x. It is positive semi-definite if this quadratic form is greater than or equal to for all non-zero x. It is called negative definite if the quadratic form is less than 0 for all non-zero x. It is called negative semi-definite if the quadratic form is less than or equal to 0x. And, well, it's called indefinite. We don't know what the heck's going on. If the quadratic form is greater than 0 for some value of x, and it's less than 0 for some other value of x. So now let me explain the Hessian. And so the matrix representation for the second derivative, the second differential of f at A. It's called the Hessian matrix, and it's denoted by f sub f at A. We usually suppress the A in the notation. So, f h sub f. So I usually don't put the A there. Just because it's, I don't know, it looks weird. So the Hessian matrix, let F go from Rn to R. The Hessian matrix of F is the Jacobian matrix of the gradient vector. Okay. Okay, well, so sometimes we denote, well, the determinant of that. I'll just, I sort of repeated what I said here. Let me just sort of erase that. Oh, I see. Okay, come on. Okay. Let's just, if I can. Why is it not? Oh, here it is. Okay. Let me just get rid of that. Okay, so there. So the Hessian of F is just the Jacobian of the gradient vector. It is the matrix whose ith jth entry is the second partial of F with respect to xj and xi. And so, let u and v be unit vectors, then, and this is, so notice that this will be a quadratic form. Okay, then the directional derivative in the direction of the directional derivative in the direction of u of f is just the transpose of u times the Hessian matrix times, so thus du f, which is u transpose h, will be a quadratic form. Okay. Let V and W be norm vector spaces, complete norm vector spaces, so Banach spaces, and let F go from V to W, be continuously differentiable. If the second derivative d of f at a equaling our notation d squared f at a exist, then for each fixed u in the vector space V, the function going from V to the directional derivative in the direction of u of f of V from, so this is just the directional derivative, from V to W is differentiable at A, and this is what we said here. The directional derivative in the direction of V of the direction of f at A is just this second partial, the second derivative of f at A evaluated V evaluated at U. You remember it's a linear function of a, it's a linear functional of a linear functional. So it's a linear transformation of a linear transformation here. So the second derivative test says, and let's assume that f is continuous at A. Says if the first differential of f at A is 0, and if the second differential of f at A is negative definite as a quadratic form, what we've seen above, on V, then we have a local maximum at A. If the first differential of f at A is 0, and the second differential of f at A is positive definite as a quadratic form on V, then we have that this is a local minimum. Oh, I should note that I did tell you how to show that they were definite, to show they're positive definite or negative definite. Well, if the first term is positive, then it's positive definite. The first term is negative, it's negative definite. Second derivative test. Okay, so let me formulate the second derivative test. Let A be open in a real normal vector space X. Let f go from A to R, be twice differentiable, with the differential of f at A being 0, where A is in the set, is in the vector space A. If the second derivative of f at A is positive definite for x near A, then A is a local minimum. So let's further refine this. Let's do it for just the two variable case. Suppose the second partial derivatives of f going from R2 to R are continuous on a disk with center AB, and suppose that the partial of f of x at AB is 0, and the partial of f of y of the partial of f respect to y at AB is 0, then the discriminant, sometimes denoted the discriminant at AB, then if we let the discriminant be defined as the second partial of f with respect to x at AB times the second partial of f with respect to y at AB minus the product of the mixed partials of f at AB. Then we have the following. Remember, if the discriminant was greater than 0 of this quadratic form. And so that will tell me if the sign is greater than 0, then it's a local minimum. If the sign is less than 0, then it's a local maximum. If this discriminant was less than 0, we didn't know what the heck was going on. So it'll be the case where well, on one side it'll be increased, it'll be look like a maximum, but on the other side it may look like a minimum. So let's do this. If the discriminant is greater than 0, this product here, and if the second partial of f with respect to x at AB is greater than 0, then f at AB is a local minimum. If the discriminant is greater than 0, and if the second partial of f with respect to x at AB is less than 0, then f at AB is a local maximum. If the discriminant is less than 0, then f of AB is a saddle point, meaning that in one direction it looks like a maximum, but if you go in a different direction, it looks like a minimum. So you can think of it as you are walking on some mountain, and you get up to this place where you look and you're in one direction, you seem to be in a valley, but if you look in this different direction, you seem to be at in one direction you're always going down, whereas in another direction, if you turn, you're always going up. So in one direction you're sort of a minimum, the other direction you're sort of a maximum, but you're neither a maximum nor a minimum. You're a saddle, meaning that, well, if you're sitting in a saddle on a horse, well, in one way, when your legs hang over the side, so that's a maximum. But in the other direction, where you're still, it's curved so that you don't fall out of the seat, out of the saddle, well, it's a minimum. So that's why we call this saddle point, because if you look at a saddle, that point that you sit on is called a saddle point. Okay, so let's further. In general, suppose f is continuous at A, then if the first differential at A is 0 and the second differential at A is negative definite as a quadratic form, then we are at a local minimum. If the first differential is 0 and the second differential is positive definite as a quadratic form, then we are at a local minimum. Let me quickly restate that. So let A be an open set in a real norm vector space, X. Let F go from A to R, be twice differentiable, with the first differential being 0 at A. If the second differential is positive definite for X near A, then A is the local minimum. So let's restate that. And of course, if it's negative definite near X equal A, then it's a local maximum. I don't know why I only stated it as a minimum, but in the two-dimensional case, we have the following. So suppose suppose the second partial derivatives of f going from R2 to R are continuous on a disk with center AB, and suppose that the first partial of f respect to x and the first partial of f respect to y at AB is 0. Let D equal the second partial of f respect to x at AB times the second partial of f respect to y at AB minus the product of the two mixed partials at AB. If this determinant is greater than 0, this is actually the determinant of the Hessian. So if the determinant here of the Hessian is greater than 0, and the second partial of f respect to x at AB is greater than 0, then f at AB is a local minimum. If the determinant of the Hessian matrix at AB is greater than 0, and the second partial of f respect to x at AB is less than 0, then f at AB is a local maximum. If the determinant of the Hessian is less than 0, then f at AB is a saddle point. So that's where we ended last time. So note, D is the determinant of the Hessian. It is the determinant of the following matrix, Hessian matrix: f sub xx, f sub xy, f sub yx, f sub yy. It is the product. If I take this determinant, the second partial of f respect to x times the second partial of f respect to y minus the product of these mixed partials. The Hessian matrix is positive definite when, and that's how we got the above conditions, the determinant of this Hessian matrix is greater than 0, and so if this whole determinant is greater than 0, and if this little determinant of this minor, the second partial of f respect to x at AB is greater than 0. The Hessian is negative definite when this whole determinant of the Hessian is greater than 0, and the determinant of the minor here, matrix, the second partial of f respect to x at AB is less than 0. The Hessian matrix is neither positive semidefinite nor negative semidefinite when this full determinant is less than 0. There are additional inconclusive statements in the second derivative test, and we'll be stating those. If the Hessian matrix is positive semidefinite, but not positive definite, then the test is inconclusive, but F cannot have a local maximum at AB. So it can either be a saddle point or a local minimum, but it cannot be a local maximum. Oh, what does it mean to be semi-definite? To include the possibility of equaling 0. Yes, so sorry about that. So it is positive definite if it's greater than 0. Positive semi-definite greater than or equal to 0. So semi means it could equal 0. Kind of like if you say greater than 0, less than or equal to 0, that's what I mean by semi-definite. Sorry about that. I forgot. Yeah, I think I may have stated that. Okay, good call. Okay. So this occurs when the determinant of this Hessian, the full Hessian, D is equal to 0, and either the second partial of f respect to x is greater than 0, or the second partial of f respect to y is greater than 0. If the Hessian matrix is negative semidefinite, but not negative definite, then the test is inconclusive, but F cannot have a local minimum at AB. This occurs when D is 0 and the partial of F, the second partial of F respect to X is less than 0, or the second partial of F respect to Y is less than 0. If the Hessian matrix the Hessian matrix is both positive, semi-definite, and definite, then the test is inconclusive, but nothing can be ruled out. So this occurs when D is 0 and the second partial of F respect to X is 0 and the second partial of F respect to Y is 0. And so we've seen that say in the one variable case, say when Y is equal to, let's say, X to the fourth, it's a maximum, or negative X to the fourth, it's a minimum, or let's see, X cubed would also work, or X cubed where it's neither maximum nor minimum, a saddle point or inflection point, which what we called in the first variable case. Okay. The second derivative test in, well, more than one variable. And so it could be several variables. So let me restate this. And it'll look very similar. Now, we have to take into account all these sort of differing situations. So suppose the second partial derivatives of F going from Rn to R are continuous on a disk with center at A. And suppose that the gradient of F at A is 0. Let H denote the Hessian matrix. Then H is positive definite, implies that H has a local minimum at A. And so we can think of this as in the one variable case where if it was concave up, it had a minimum. So this will occur when all the principal minors have positive determinant. So if you look at the Hessian and you start taking determinants starting in the upper left corner. So let me move up for 1 second. So notice when we gave the second derivative test in two variables. Stop, please. Let's go back. There, okay, got it. So notice that if this was positive, so I only looked at this corner, and then I went for a bigger corner. So this corner, positive. This corner, including all these from here above, is positive. Oops, here it is. Then it was positive definite. And so it's the same sort of condition that we had from the from here. So it's the same condition that we had. It's just now we have to do it. There could be, it's an n by n matrix. Stop. Okay. Okay. So here it is. So again, we're at this place where the gradient is 0. If all the principal minors have positive determinant, then we are at a local minimum. So second, if H is negative definite. Remember, in the two-dimensional case, it was negative definite. If this first minor was negative, then the second minor, which turned out to be everything, was positive. So it went negative, positive. So it seems to be alternating sign. So H is negative. H being negative definite implies that F has a local maximum at A. This occurs when the sign of the determinant for all the principal minors are equal to -1 to the order of the minor matrix. In other words, when minus H is positive definite. So what you're doing here is you start out, for the first one, it's negative, the second one positive, third one negative, fourth one positive. And so as you keep going, they alternate in sign, and they're starting from negative, and they alternate as you keep getting bigger and bigger. That's what this means. H being positive semi-definite, so greater than or equal to 0, but not positive definite matrix. Then the test is inconclusive, but F cannot have a local maximum. It's positive. Cannot have a local maximum at A. So this occurs when all the principal minors have non-negative determinants, and at least one of the determinants is 0. And at least one of the determinants for an object. So that was the same case that I've been talking about in 2 dimensions. Okay, so H being negative semi-definite, but not negative definite, implies that the test is inconclusive, but F cannot have a local minimum. And this occurs when minus H is positive semi-definite, but not positive definite. So I just sort of put it in this other case. And then lastly, H is neither positive semi-definite nor negative semi-definite. Then F has a saddle point at A. And this occurs when none of the above cases hold examples. So there, I gave you a lot of conditions. Let's see how this actually plays out. In problems 5 through 20, find the local maximum and minimum values of the function. If you have 3-dimensional graphing software, graph the function with domain and viewpoint that reveal the important aspects of the function. Okay, so let me do problem number 10. F of x, y is equal to 2 minus x to the 4 plus x squared minus y squared. So first off, let's determine the critical numbers. So to determine the critical numbers, I want to determine when, just doing red, the gradient is 0. So I want to determine all A and B would satisfy that. So let's take the partial of f respect to x, negative 4x cubed plus 4x. Partial of f respect to y, negative 2y. Okay. So now let's set the first partial is equal to 0. Actually, let's do this one first. That says that negative 2y is 0. So y is 0. So that's good. Next, let's set partial of f with respect to x equal to 0. And so this is equal to, oops, actually let's do here, then new page. Okay, so this says that negative 4x cubed plus 4x is 0. So negative 4x x squared minus 1 is 0. And so since the polynomials over the integers are an integral domain, it says that this is 0. So either x is 0 or x is equal to plus or minus 1. So my critical numbers are 0, 0, negative 1, 0, 1, 0. Okay, so those are my 3 critical numbers. Okay. Or where this doesn't exist. We're actually trying to find where the rank of the where this is not invertible. So it could be invertible where the rank is not of the correct size for this matrix. Okay, so well, this always exists, so this doesn't give us anything at all. The gradient being 0, not existing, doesn't give us anything because the gradient exists everywhere. Okay, so since there are no places where the gradient doesn't exist, I can actually use the second derivative test. So I can use the second derivative test. So let's use it. As usual, the second derivative test is actually easier than the first derivative test. So you use the second derivative test when you can, but as always, the second derivative test has lots of conditions. And so this is because all critical numbers, for all critical numbers. Well, maybe I just say critical numbers like that. Okay, so I'm able to use the second derivative test. So I guess let's first try to determine my Hessian matrix. That's which you usually call F. H, I'll suppress all the subscripts, I guess. Okay, so let's do some more new pages. So let's take the partial of the second partial of F with respect to X. Well, this is going to give you negative 12 x squared plus 4. Since I have negative 4x cubed plus 4x. The partial of partial respect to y, well, there was no y term, so that's 0. The partial of y partial of just involved a negative 2y, so this is going to be 0. The partial of f respect to y, the partial of negative 2y was just negative 2. And so my Hessian matrix is just going to equal negative 12 x squared plus 4. That gives me a 0, and a negative 2. Okay. So let's try to conduct some tests for the critical numbers. So let's conduct the second derivative test. Let's say at 0, 0. Okay. So if I plug in 0, 0, the Hessian is going to be a 4, 0, 0, negative 2. Okay. Okay, so I'm going to be looking at, come on. So I'm looking at D, the determinant of this Hessian matrix. And so the determinant is just going to be 4 times negative 2 minus 0 times 0. So the determinant of the Hessian matrix is negative 8, which is less than 0. Okay. And if I look at the first minor, which is the 4, and so if I look at, well, the first principle of the first minor, so the determinant of the principal minor of the first principal minor of H. Of course, I'm probably, oh, good, okay. I didn't use H for, there's an unfortunate habit for us to call H both the matrix and the determinant of the matrix in this case, determinant of the first principal minor of H is 4, which is greater than 0. And so is, maybe I'll write it this way, 4, and this 4 is greater than 0. So we're at a saddle point. So the saddle point when, well, at 0, 0. Or f of 0, 0. Maybe I'll say f at 0, 0, which is 0 actually. So we're at a saddle point. Well, even though it's a value, I'll call it a saddle point when x, y is 0, 0, and its value is f of 0, 0. Okay, so let's conduct the second derivative test. Actually, they're both going to be the same. Well, yeah, they'll both be the same. Let me just say plus or minus 1. And this is because we can do this because H involves only x squared. It's going to square everything. It doesn't matter if it's positive or negative 1. Let me put in one more page. I think that's probably it for that. Okay, good. Okay, so let's figure out what H is. So H is negative 12 x squared plus 4, 0, 0, negative 2. Okay. So H is equal to negative 8, 0, 0, negative 2. Okay. So now, let's show that this is negative definite. So if I look at the determinant of the first of these principal minors, well, it's just going to be negative 8, which is less than 0. Let's take the next determinant, which we actually called D, which is going to give us negative 8 times negative 2 minus 0 times 0, which is greater than 0. So it alternates, and then alternating after that in sign. So it goes negative, positive, and so therefore we're negative definite. So F is negative definite. At 1, 0, plus or minus 1, 0. So that says that we're at a local maximum. Oh, maybe I'll say this F, This sounds better. When at plus or minus 1, 0. So I have two local maximums. And that is your answer. Maybe that sounded better. F has a, I'll change this. F has a saddle point. When, yeah, the when doesn't sound good. At 0, 0. Okay. So F had a two local maximums, one at negative 1, 0, another at 1, 0, and a saddle point at 0, 0. Okay. Let me do problem number 18. So same instructions. So let's determine the critical numbers. So I want to find where the gradient is 0. And where this gradient doesn't exist. Obviously, the gradient is never going to be, never. Okay, so let's do that. So let's take the partial of f respect to x. Product rule, drew of the first times the second plus the first times the derivative of the second. The derivative of e to the minus x is e to the minus x times the derivative of the exponent, which is negative. So that's why there's a minus there. And so let's take the and maybe I'll write it this way. Let's factor out e to the minus x. So 2x minus x squared minus y squared e to the minus x. Let's take the partial of f respect to y. And so again, oh, well, this is just the derivative of x squared plus y squared is 2y times the constant e to the minus x. Okay. Let's set each of these equal to 0. And so partial of f respect to y equaling 0 implies 2y e to the minus x is 0. It can't be 0, neither can e to the minus x. So y is 0. And let's set f sub y equal to 0. Okay. So now let's set partial of f with respect to x equal to 0. So I get 2x minus x squared minus y squared e to the minus x is equal to 0. Okay. And so y is 0. So I get 2x minus x squared e to the minus x is 0. Obviously, e to the minus x can't be 0. And so I have that either x is 0 or x is equal to 2. So I get that 0, 0, and 2, 0 are critical numbers. And we can't have that the gradient is not 0, doesn't exist, because all those inside the gradient were nice and defined everywhere. So I can either use first or second derivative test. Let me show the first derivative test. Why? Just because I did the second derivative test on the other one. So let me conduct the first derivative test. Just because it's good to show you both tests. And so that's really the only reason for showing first derivative. Okay. So let's conduct the test at 0, 0. So let's do that at the origin. So I want that the gradient of f at xy dot the gradient dot I want that this is somehow going to be greater than 0 or less. Somehow I can find, and this will be near the origin. So I want to show that this has some definite sign near the origin. So for xy near 0, 0. Okay, so let's look at this. And so the gradient was 2 minus, so 2x minus x squared minus y squared e to the minus x, 2y e to the minus x dot xy. Okay. So this is equal to, well, let's just multiply that out. So this is going to be 2x squared minus x cubed minus xy e to the minus x plus 2y squared e to the minus x. Okay. So this is equal to 2x. No, let's do an x. squared, 2 minus x. Let's factor out first just e to the minus x. 2x squared minus x cubed minus xy plus 2y squared e to the minus x. Just factoring out e to the minus x. Okay, so this is equal to, let's sort of factor by grouping. So let's say 2x squared minus x cubed minus xy minus 2y squared e to the minus x. Factor out x squared. That's a 2 minus x. Factor out y. Actually, I wonder if I can switch those around. That would give me something better. Factor out a y. Gives you x minus 2y. Okay, 1 second. That didn't work. Ooh, wait 1 second. That's a y squared. That was y squared there. That was y squared. Y squared. Ooh, this is a y squared. Oops. E to the minus x. That does work. Okay, so now, so this then looks like x minus, or 2 minus x. And so switch that order, that'll make that a plus. X squared plus y squared, which is good. E to the minus x. Okay, so certainly x squared plus y squared, that's always going to be positive. E to the minus x is always positive. All I have to have is that 2 minus x to have that as a definite sign. Well, we can certainly have that that's greater than 0. Oops. As long as x is small, this will be greater than 0. For x, well, less than 4 or something. So as long as we're close, as long as x is less than 2, we're certainly going to be greater than 0. So if we're close to the origin, certainly if we're within 1 of the origin, this is going to be positive. And so therefore, by the first derivative test, so we're always greater than 0 near there. So that means we're at a local minimum. Yeah. So F has a local minimum at 0, 0. I do have it in. Okay, wonder why that's telling me that. Okay, has a local minimum. At the origin. Okay. Since that is always greater than 0, meaning we went from decreasing to increasing, so it's a local minimum. Okay, good. Let's conduct the test at the other point. So let's conduct the first derivative test. At 2, 0. And so we want to show that the gradient of f, so nabla f xy dot xy minus 2, 0. I want to show that that has some sign, if that has some sign. Okay, so this is for values of x and y that are close to 2, 0. Okay, so this is just, what was it? 2x minus x squared minus y squared e to the minus x, 2y e to the minus x dot x minus 2y. Okay. Let me just check. It was an x. It was a 2y. It was a 2y. And okay. Okay, so let's multiply this. Actually, I wonder if that's a 2 minus x. Let me write it this way, because that will give me maybe something. This is a factor out of minus x times x minus 2 e to the minus x minus y squared e to the minus x. That could make my life a little easier. So this is equal to multiply this. So this is equal to a minus x minus 2 squared e to the minus x minus x minus 2 y squared e to the minus x plus 2y squared e to the minus x. So this is equal to these, that's a minus and a minus. So that becomes a plus. So this is equal to a minus x minus 2 squared e to the minus x minus +2 plus 2 is +4. Y squared e to the minus x. Okay. So now so if I look here, well, this term here is positive. This term here is positive. So the x minus 2 squared e to the minus x are positive. Y squared e to the minus y minus x is positive. But I have here these quantities. So for x near 0, so notice that this is greater than 0 for x greater than 0, let's say negative. For x less than 0 and small. For small x less than 0. So in this case, this is going to be positive for small x less than 0, but it's going to be for small x greater than 0. So because of that, this is actually going to change sign depending on how close you are. And so therefore this doesn't have a definite sign. It actually changes sign. And so this is going to change sign. So therefore F has a saddle point at was it 2, 0. And so since it was neither positive, since it changed from positive to negative, then that means that it's not, it's going to be a saddle point. Okay. Let me do 36. Actually, I'll let it one more down. In problems 31 through 38, find the absolute maximum and minimum values of f on the set D. So now what we're going to do is we're going to try to maximize a function, a continuous function on a closed region. And so to do that, well, we want to find the maximum and minimum, the extrema, on the boundary and the extrema in the interior. And then the extreme, which of the extrema which of the extrema on the boundary and interior will actually be global extrema. So first, let's determine the interior critical numbers. So when we did this in the one-dimensional case, we first looked at the interior interior critical numbers. Then we endpoint extrema. These will be the boundary extrema. And then saw which one, compared and checked to see which one was actually the actual extrema. So let's determine interior extrema. Determine interior critical points, critical numbers. Okay. So I want to determine where the gradient is either 0 or where it doesn't exist. Okay. Well, it's obviously just going to be where it's 0. So let's take the partial of f with respect to x, y squared, partial of f with respect to y, 2xy. Set the first partial of f with respect to x equal to 0. So it says that y squared is 0, so y is 0. Okay. And now let's set the first partial of f with respect to y equal to 0. It says that 2xy is 0. So x times y is 0, but y is 0. If y is 0, it doesn't really matter what x is. So in this case, we have a lot of critical points. And so this just says x can equal anything. And so so critical numbers. Well, maybe I'll just say that the critical numbers are x 0. Okay. So let's try to look at the, oops. Yes. Okay, so, well, actually, what it means is that, let me just check. So it means that along, so it's 0. Oh, so that's the boundary. So 0 is the boundary. Oh, yes, it does. Sorry. So it means that that in this case, it's along the boundary. So the critical numbers, sorry about that, you're absolutely correct. So the critical numbers are along the boundary. So what it says is that our critical numbers but these are along the boundary. Are along the boundary. Which implies no interior. Well, of course, that these are not interior critical numbers. Since they're not interior. Let's look when the gradient doesn't exist. Well, the gradient exists everywhere. Therefore, now we can say there are no interior critical numbers. Okay, good. So we don't have to look at the interior. We only have to look at the boundary. And so because of this, we just have to optimize along the boundary. Okay. So let's look at the boundary. So my boundary was this. Maybe let's draw this. Okay, so x squared plus y squared is 3. Okay, so let's make it a little bit bigger. So there. So this is rad 3. This is rad 3. It's 0. So this was my boundary of my region. This is called D, my region D. And so I just want to, so before it was saying, was X was anything. So we first got that there were some critical numbers here, but we didn't care because that was a boundary. And so I have to look at this whole thing. So let's try to optimize. And we'll probably split this into differing regions so that I can try to optimize it. So let's optimize on the boundary let y equals 0. So x 0, where y is between 0 and rad 3. So it's optimized on our region. Okay. So I have here f of x, y, which is just x times y squared. So this is always equal to 0. Okay, so I know that along this boundary, it's always going to be 0. Let's look at this other boundary. Well, that's probably also going to be 0. So let's optimize on the boundary. Zero y, or y is between 0. Wait, that was stupid. That was not, that was an x, where y is between 0 and rad 3. Okay. So I want to optimize along that boundary. Okay, so f of 0y is going to be 0 y squared, which is 0. So far, these boundaries were rather look at this quarter circle. So optimize on the boundary. XY. Where x squared plus y squared is equal to 3, and x, you can say greater than 0 or greater than equal to 0, doesn't really matter. Y greater than equal to 0. So along this. Now, of course, you've already tested these endpoints, so it doesn't matter if you include the endpoints or not. The endpoints, they'll be 0, so it doesn't really matter. Okay, so let's do this. So this is f of xy is xy squared. One more page. Okay, so this is equal to, and it really doesn't, this is y squared. So let's write this in terms of x squared. So x and then y squared is, well, plus or minus the square root of 3 minus x squared. I'm actually just going to be using the fact that y squared is 3 minus x squared. Okay, so yeah, I don't like that notation. So this is equal to x times 3 minus x squared. I'll just say over here, since y squared equals 3 minus x squared. So now this is 3x minus x cubed. So let's try to somehow optimize this. Okay, so let's try to optimize. Oh, actually, since it's greater than 0, it would have been a positive. Actually, it would have been a positive square root. So it didn't matter because of this condition here. It would have taken a positive square root. Okay, so I want to optimize. So let's determine extrema. Oh, come on. Determine extrema. For, I don't know, let's call it g of x equaling 3x minus x cubed. Okay. So I'll take the derivative. And so this is going to be 3 minus 3x squared. Second derivative minus 6x. And so first derivative equaling 0 says that x is equal to plus or minus 1. Okay. Okay. Almost done. Just like 1 more minute. If I can move this. Oh, come on. Just struggling to move. Thank you. Oh, come on. Okay. Got one finally. Okay, good. So the second derivative at minus 1. And of course, the first derivative always exists, so I don't have to worry about that. And so this is equal to a plus x. It's greater than 0. So at minus 1, it's going to be a local a minimum. Actually, it doesn't matter. Okay, so the critical numbers, actually, we're doing this. Okay. We don't even have to, we just, because we're going to check these everywhere, anywhere. Anyway. Because we're doing this on a boundary. Okay, so I have that 3 minus 3x squared equaling 0 says that x is equal to plus or minus 1. So let's figure out what f is at 1, and we can do that. We can do it at plus or minus 1, yes. So let's figure out f. So now, when x is equal to negative 1, actually, it doesn't really matter. What is y? Y is equal to plus or minus rad 2. Okay, so now let's figure out what f is at negative 1 rad 2. And x can only be greater than or equal to 0. Stupid. So x can only be greater than or equal to 0. I'm trying to do this too fast. So x is only equal to 1. And so y at that point is equal to positive radical 2. Okay. And so let's figure out what f is at 1 radical 2. It's equal to 2. Okay. So we get the following kind of strange situation. So we get an absolute maximum or global, let's call it a global maximum. value of f is 2 is equal to 2 when at 1, 0, 1 rad 2, and I'll have to say the other part. And we have a global minimum and a global minimum value of f of x y is equal to 0 along the other parts of the boundary on well, let's say x, that first boundary, which was x's were between 0 and rad 3. And the other boundary where it was 0, y, and y's were between 0 and rad 3. So along those two boundaries, the function was always equal to 0. And so we had the global minimum value of 0. Problem number 50. Find the dimensions of the rectangular box with largest volume, 64 square centimeters. So suppose I have some rectangular box and it has length x centimeters, y centimeters, z centimeters. And so I want to maximize the volume. And well, the volume of a rectangular parallelepiped is just length times width times height. And this is going to be subject to the following constraint, that the surface area, well, the surface area, rectangular box, is, well, let's see, the volume, the area of the bottom, length times width, so that's just xy, but the top is also xy, so it's 2xy. The area of the side is yz, but on this side, it's also yz. It's 2yz. And the area of the front face is xz, and the back face, it's also xz, so 2xz. And that should equal a surface area 64. Let's divide each of these by 2. So if I do that, I just get xy plus yz plus xz equals 32. I can solve this. Well, and besides that, I'm also going to assume that x, y, and z are non-negative. Are actually greater than 0. If they're equal to 0, if any of these are equal to 0, then the volume is going to be 0. And so we're, at least for in the first octant, we're not going to have a maximum along this boundary where any of the variables are 0. It'll be a minimum, actually. And so along that if I'm restricting it to that closed boundary. So in order to maximize this, let me just assume that each of these are variables are greater than 0. So if I do that, notice that in this case, for any variable in terms of the others, let's solve for z, because that's a nice variable to eliminate. So I'll factor out a z. Subtract, x, y from both sides of my equation. And then divide both sides of my equation by x plus y. So z is equal to 32 minus x y. So now let's plug that back into v. So I want to maximize v, which will equal xy times z, which is 32 minus xy over x plus y. So I'll be wanting to maximize this. So so now v here is just a function of x and y. So I want to maximize some function of two variables. Actually, let me rewrite v as, let's multiply the xy inside the parentheses, 32xy minus x squared y squared over x plus y. Okay, so I want to find the extrema for this function, assuming that both x and y are greater than 0. And so, and z is greater than 0. And so let's try to determine the critical numbers. So let's take the partial of v with respect to x. So the derivative of the numerator, 32y minus 2x y squared, times the denominator, x plus y, minus the numerator, 32xy minus x squared y squared, times the derivative of the denominator, 1, all divided by the denominator squared. Let me multiply x plus the 32y minus 2y squared and distribute it with the x plus y. So this is partial v with respect to x is 32xy plus 32y squared minus 2x squared y squared minus 2xy cubed. Change all the signs inside the parentheses, minus 32xy plus x squared y squared, all divided by x plus y quantity squared. So let's combine like terms. So the partial v with respect to x is equal to 32, and so the 32 xy's cancel. So this is equal to 32 y squared. I have a minus 2x squared y squared and a plus 1x squared y squared. So that's a minus 1 x squared y squared minus 2 xy cubed, all divided by x plus y, 20 squared. Let's find the partial v with respect to y. So it's going to be the derivative of the numerator. This is all symmetric. And so it's going to be 32x minus 2x squared y times the denominator, x plus y, minus the numerator, 32xy minus x squared y squared, times the derivative of the denominator, which is just 1, all divided by the denominator squared. And so I have the partial of v with respect to y is equal to, again, let's multiply this out. So it's a 32x squared minus 32xy plus 32xy minus 2x squared x cubed y minus 2x squared y squared minus 32xy plus x squared y squared over x plus y quantity squared. So partial v respect to y curly v curly dy. Okay, so this is equal to 32x squared. The 32xy's cancel. Minus, well, let's make it symmetric. Minus 2x cubed y. I have a minus x squared y squared plus x squared y squared all over x plus y quantity squared. Okay, so first let's set the first partial of v with respect to x equal to 0. I want the gradient equal to 0, so I want the partial of v, well, with respect to x equals 0. And so I'm going to set the numerator to 0. And so I just get 32 y squared minus x squared y squared minus 2x y cubed equal to 0. And remember, these were symmetric. They look the same. Under a transformation replacing x by y. And the partial v with respect to y equaling 0. Said that. Again, I'm assuming that the and so I have 32 x squared minus x squared y squared minus 2 x cubed y equals 0. Okay. So now, let's try to solve this. So let's multiply this first equation by, well, actually, let's factor out. Okay. Okay, so I have here that this first equation is just 32, oops. It's 32 minus x squared minus 2xy. Y squared is 0. But I'm assuming that y is greater than 0. So that says, so that says that 32 minus x squared minus 2xy must be 0. And similarly, from this equation, let's factor out x squared. So I have 32 minus y squared minus 2xy, x squared equals 0. Again, x is greater than 0 by my assumption. And so x squared cannot equal 0. So 32 minus x squared minus 2xy must equal 0. Okay. So I now have two equations and two unknowns. So I have x squared plus 2xy is equal to 32. And I have y squared plus 2xy equals 32. So I can just subtract these, actually. And most everything will cancel. So I get that x squared minus y squared is 0. And so let's factor that. So I get x minus y times x plus y is equal to 0. So I get x minus y is 0, or x plus y equals 0. So I get y is equal to x, or y is equal to negative x. But x must be positive. And so if x is positive, then negative x is negative. So that gives me a contradiction. So that can't happen. And so I have that y equals x. Okay. And so let's plug that back into here. And so x squared plus 2xy is equal to 32. So that says that 3 x squared is 32. So this says that x is equal to plus or minus the square root of 32 over 3. But now I'm assuming x is greater than 0. And so that says that x is equal to square root of 16 is 4. 4 rad, let's write it this way. X is equal to 4 times rad, take away 16, 2/3. Okay. But y is also equal to x. So y is also equal to 4 times the square root of 2/3. Okay. But z, well, maybe we'll figure out z at the end. Z is going to be equal to the same thing. So let's use, well, now let's set the gradient. So those are so that gives me these critical numbers. So now let's see where the gradient does not exist. And see what happens there. Well, the first partial of v, we expect x not equaling 0, or the first partial of y not existing, says that, well, x plus y is 0. Since both of these are rational functions in x and y, and the denominators are the same, they're both x plus y. So the only way that these first partials can exist is if you're dividing by 0, which in this case is that x plus y is 0. But if x is positive and y is positive, you can't have that. It gives you nothing. So therefore, my critical numbers are 4 rad 2/3, 4 rad 2/3. So those are my two critical numbers. Since these critical numbers were found by setting the first derivative 0, well, I can use the second derivative test. And so let's use the second derivative test. And so let's first compute the Hessian. Or, yeah, compute the Hessian. Okay, so everything's nice and symmetric. So let's take the second partial of v with respect to x. Okay, so let me just cheat for 1 second. Even though I know they're symmetric, I have to remember what they look like now. There it is. So let's take this guy. And let me just store it for a second so I can see it somewhere. Okay. So let me just put it up here. Okay, so derivative of the numerator minus 2 x y squared minus 2 y cubed times the denominator x plus y squared minus the numerator 32y squared minus x squared y squared minus 2xy cubed. Let's bring down the 2. Subtract 1 from the exponent times the derivative of what's inside, all divided by the denominator squared. Let's cancel one of these. So this is equal to, I don't need this anymore, even though y is going to look almost identical. Actually, I don't even have to separate down the y because it'll look the same. So this is the second partial of v with respect to x. Let's multiply this out. So it's a negative, it is a negative 2x squared y squared minus 2xy cubed minus 2xy cubed minus 2y to the fourth. Multiply negative 2 inside the parentheses. Negative 64 y squared minus, and the minus is a plus, 2x squared y squared plus 4xy cubed, all divided by, okay, all divided by x plus y quantity cubed. And so this is equal to, okay, 1 second. Let's see if it'll give me back control. So this is equal to the second partial. Okay. Second partial of v with respect to x. Okay, let's cancel. The minus 2x squares cancel. That becomes a 4. Oh, and so there are 4 of these, which cancel with 4 of those. So everything cancels except for those 2 terms. So this is a minus 2 y to the fourth minus 64 y squared over x plus y cubed. Okay, so actually maybe I'll evaluate this at rad 32. So this is, let's evaluate this at 4 rad 2/3. Okay, so, oh, actually I should, it'll be easier to make to not simplify this. It'll be easier to write it this way. It'll be easier to evaluate at rad 32/3. Okay, so this is equal to minus 2. This will be 32 squared over 9. Minus 64, 32 squared. 32/3 divided by x plus y, so there could be 2 of these rad 32/3 cubed. Okay. So this is equal to, let's evaluate this. And so, 32 times this, okay, that'll give you a 64. Okay, good. So I can I don't need to figure out what 32 squared is because I can just write 32 times 2. So that's what gives me a 64 there. So this is a negative 64 times 32 over 9. So minus, so make this a multiply by 3. So that's 192, 32 over 9. And then cube that, so that's an 8. And then this will be 32 over 3, if I square it, times rad 32 over 3. Okay, so some things will cancel. The 32s will cancel over 3s. So these will just become 1/3. So this will cancel with these and give me a 1/3. Okay. And so this is equal to partial, the second partial of v with respect to x at this rad 32 over 3 gives me a negative 256 times 1/3 over 8. So that'll simplify that over rad those were both minus. I'm just checking something just to be sure my signs were correct. Yeah, they were all minuses. Okay. And this is 32. Over 3. Okay. Maybe I'll multiply and divide by rad 32 over 3. See if this will help me. Rationalizing my denominator. In this case, might actually make the calculation easier. Okay. Because then everything cancels, doesn't it? Then this becomes second partial of v respect to x at rad 32 over 3. You just get 8 times 32, but that's 250. So this is 256 times 1/3 over, and this is rad 32 over 3. 8 times 32 is 256, and then rad 3 times rad 3 is 3. So these actually just cancel. And so you get, oh, it's the same thing. So you get the second partial of v with respect to x at rad 32 over 3. Rad 32 over 3 is just minus rad 32 over 3. Okay, good. Let's take the mixed partial. So let's take this mixed partial. So let's take the mixed partial. And so I get derivative of the numerator, 64y minus 2x squared y minus 6xy squared times the denominator, x plus y quantity squared, minus the numerator squared minus x squared y squared minus 2xy cubed times the derivative of the denominator. Oops. So bring down the exponent. Rewrite the quantity inside the parentheses to the power of 1 less times the derivative of what's inside, all divided by the denominator, x plus y, squared, and square that. So x plus y to the fourth. Okay. And so, error. So, let's simplify this. Oh, first let's cancel out one of these, x plus y's. And so I get that the mixed partial is equal to 64y minus 2x squared y minus 6xy squared times x plus y minus, let's multiply the negative 2 inside the parentheses. So minus 64y squared plus 2x squared y squared plus 4xy cubed divided by x plus y quantity cubed. And so let's simplify this. So let's multiply each of this first term by x plus y. And so I get that the mixed partial multiply, and so I get a 64xy plus 64y squared minus 2x cubed y minus 6x squared y squared. Wait. Minus 2x squared y squared minus 6x squared y squared minus 6xy cubed minus 64 y squared plus 2x squared y squared plus 4xy cubed, all divided by x plus y cubed. And so the mixed partial 64 xy doesn't cancel with anything. So 64 xy. The 64y squares cancel. 2, so x cubed, nope, that's it. So plus, minus 2 x cubed y. Okay, so that remains x squared y squares Oh, some of them cancel. So these twos cancel, but you get a minus 6x squared y squared. And you get some cancellation here. Minus 6 xy cubed and a plus 4 gives you a minus 2 xy cubed, all divided by x plus y cubed. Okay, so now let's evaluate this. And yeah, again, it'll be easier to evaluate it at rad 32 over 3. So this will give you 64. That'll just be a square. So this is 32 over 3 minus 2. This will give you 4 of them. So this is a 32 squared over 9. So I can see some partial cancellation. Minus 6 x squared and y squared. So those are just 32 squares over 9. And minus 2. Again, x, y cubed, so that's another 32 squared over 9. Divided by 2 of these rad 32 over 3 cubed. Okay, so this is equal to, oops. So this mixed partial, evaluated at our critical number, is, let's put everything as a 32 over 9. Okay, so this is, oops. Let's factor out my 32 over 9. Get the screen back. Waiting for my screen. Okay, so it's a 32 over 9. Let's factor that out. And so I'll have to multiply this by 3. So that's 192 minus, I have to multiply by 32, 64, minus, have to multiply by 32, 180, 192. Have to multiply by 32, so that's 64. Over 2 cubed is 8. And then let's do the 30, let's square this. So that's 32 over 3, rad 32. Oh, let's again do the trick where 32 over 3. So some of these are going to cancel. So 32's cancel. And then this cancels with this. So I get a 3 equal to second partial at the critical number is equal to, so these cancel, minus 128. And that's multiply and divide by rad 32 over 3. Okay. So this becomes, I'm dividing by 8 and 32 over 3 and rad 32 over 3. Okay, good. So that is 256. So that's a half. That's 3 halves. Okay. So I get second partial. Hopefully no error at the critical number. Is a negative 3. And again, if I divide by 32, that's going to give me a 4. And then 8 divided by 4 is 2. So that'll give me 3 halves. We're at 32 over 3. Okay. Now let's take the second partial with respect to y. Actually, let's do the other mixed partial. Let's do the other mixed partial. Okay, so this is equal to, oh, this is x. Okay, so I'll delete that. Let me get the partial with respect to y, even though it's symmetric, just so I don't make an error. Because it has been a while. Okay, that's way up there. Here it is, right there. So that's the second partial with respect to y. Okay, so just put it up here at the top so I don't forget what it is. So this is the partial with respect to y. Okay, so oh, I'm doing the mixed partial. Okay, so let's do the mixed partial. And so let's take the derivative of the numerator, 64x minus 2xy squared minus 6x squared y times the denominator minus the numerator, 32x squared minus x squared y squared minus 2x cubed y times the derivative of the denominator. Bring down the exponent. Subtract 1 from the exponent. Oops. Okay, come on. Okay, let's see. It's doing a lot of just freezing here for a second. Okay, come on. Sorry about that. Okay, come on. Scroll. Thank you. And so this is subtract 1 from the exponent times the derivative of what's inside, all divided by the denominator squared. So x plus y squared is x plus y to the 4th. And so I get second partial of v xy equals 64x minus 2xy squared minus 6x squared y, x plus y, multiply 2 inside the parentheses, 64x squared plus 2x squared y squared plus x cubed y divided by x plus y quantity cubed. Let me multiply these first two terms together. So by distributive property, I get 64x squared, 64xy minus 2x squared y squared minus 2xy cubed minus 6x cubed y minus 6x squared y squared. Let me actually make that look a little nicer. That was a x squared y. Yeah, that was an x squared y. Okay. Minus 64 x squared 2x squared y squared plus 4 x cubed y divided by x plus y cubed. Okay, so second partial, the mixed partial. So 64 x squares cancel. The xy's, xy, 64xy, the x squares, y squares, those two cancel. So you just have a minus 6 x squared y squared. Okay. You have a x y cubed. That's only xy cubed term. You have a x cubed minus 6x cubed y and a plus 4x gives you a minus 2x cubed y. And so again, we have 4 terms, x plus y cubed. So let's try to evaluate this at my critical number. And so the partial, the mixed partial, evaluated rad 32 over 3. Rad 32 over 3. So this is equal to 64. This will give me a 32 over 3 minus 6. This will give me a 32 squared over 3 squared. So 32 squared over 9. This will give me a 2, same 32 squared over 9. This will give me a minus 2, the same 32 squared over 9, all divided by, adding up the same one, so there's 2 other rad 32 over 3 cubed. Okay, so this is equal to, let's just evaluate this. Factor out 32 over 3. What remains is, again, multiply by 32 over 9. Let's do 32 over 9. So multiply by 3, that's 1,892 minus 32 times 6 is 192. 32 times 3, 64. 32 times 3, 64. 2 cubed is 8. Let's do 3 of these, so that's actually let's multiply and divide by rad 32 over 3, in which case this becomes rad 32 over 3 squared, so that's a 32 squared over 9. Okay. So this cancels out one of these. And it cancels out a 9. Okay. So this is equal to, scrolling back up, I get that this is equal to, so the mixed partial. Okay. Let's see if I can get control, but what the world? The screen has gone blank on me. So when I get control back, when I can get control back of this. Okay, so the mixed partial evaluated at the critical number is the 192's cancel. So I get a negative 128. That's kind of strange because now I don't get that 3 squared. Okay, so now I get 8 times 32, which is 128. No, is 256 of rad 2 over 3. Okay, so now I am getting a little worried about the previous calculation because it should have been the same, because these were the same calculation, but I got a different answer. Okay, so wait 1 second. Let me get control back of this. Okay, so this mixed partial. I have to, for 1 second, check my previous calculation. So this becomes a negative 1/2 we're at 32 over 3. Because I got a 3 halves before. Somehow I didn't get. Okay, so let's just check something. Of course, I want to get rid of this. Oh, I had a 3 there. Ooh. Which canceled with the other 3. There was a 3. Oops. There was a 3 that I didn't take account of. This 3 here sort of disappeared in my calculation, and so that's not good. So that cancels. Ooh. So, okay, so let's scroll. Oh boy. So that was a 1/2, not a 1. Okay, come on, please give me back control of my computer. Okay, so this should have been a 1/2. Oops. So this should have been a 1/2. Okay, so they're actually both the same. Good. Oh, that was a typo there for 1 second. I got a little overly excited. Okay, so, I wonder if, yeah, that's the mixed partial. Okay, so now let's do the second partial of v with respect to y. Derivative of the numerator. Oops. Derivative of the numerator minus 2x cubed times the denominator, x plus y squared, minus the numerator, 32x squared minus x squared y squared, minus 2 x cubed. Bring down the exponent, times derivative of the denominator, bring down the exponent, subtract 1 from the exponent times the derivative of what's inside, all divided by the denominator squared, x plus y to the 4th. Factor out one of the x plus y's. And so I get a freezing screen yet again. Okay, so I get that the second partial, okay, come on. I get an hourglass. Okay. And so I get that the second partial of v respect to y, multiplying this out, I get a negative 2x cubed y minus 2x squared y squared minus 2x to the 4th minus 2x cubed y, multiplying negative 2 inside the parentheses. Negative 64 x squared plus 2x squared y squared plus 4x cubed, all divided by the denominator, x plus y cubed. So this is equal to
the second partial. Why is it not being able to? The second partial, there it is, got control back. With respect to y, -2, -2. So that gives me a -4 x cubed y. Okay. One second. Let me just see something for 1 second, because that's not symmetric with my other. Oh, come on, just let me get, oh, that was a, one second, let me just check. Oh, okay. Okay. Let me just check for 1 second. I just want to see if that was symmetric. Oh, that is symmetric in that. Okay. Okay, wait, stop. Oh, that was a +2. Okay. And that was a +2. Okay. Okay, so -4 x cubed y. The 2x squares, y squares cancel. These were both negative. Okay. Minus 2x to the fourth. That was already accounted for. Minus 64 x squared plus 4 x cubed over x plus y cubed. Okay, let me just check something really quickly with the second partial with respect to x. Yes, it was this. It should be symmetric. That was a plus. Okay, and that meant that those canceled. Oh, here, wait. It meant that that canceled with the 4 of those. Okay, so let's just check why those didn't cancel. Let's just see if there was some sign error. Minus. And a minus. Ooh, I see an error, I think. Let me just check something. Come on. It should be that somehow these cancel. And so x cubed. Okay. Let me just check again. So the partial respect to y. Let me just check this, sorry. Because this should be symmetric. Okay, stop. Let me get this. Let me copy this for 1 second. Not having it readily available is a little slow. I want to check this last term. Okay, stop. Will you please stop and give me back control? Okay. Okay, so let me look at this for 1 second. Okay, -2. Oh, there it is right there. There's the error right there. Yep, because it wasn't symmetric. Okay, so hopefully now it will be. There's a y here. Okay, so that's a derivative. Okay, so and let's check the first term. That's 0, that's 2 extra, that's a 2 extra. Okay, that's all correct. And then bring down the exponent 2, x plus y times 1. And then these cancels. Okay, so the last term should have been a y. Oops. So the last term here should have been a y. Which means that these cancel. So x cubed y, there it is. So this, and this cancel. Okay. So now it's looking correctly symmetric. Okay, let's get rid of this. So this becomes negative. Oops. Oh, come on. Negative 2x to the 4th minus 64x squared over x plus y cubed. Okay, so lastly, let's evaluate this at we're at 32 over 3. We're at 32 over 3. So this is -2 to the 4th is 32 squared over 9 minus 64 times 32 over 3 divided by x plus y, that's 2, we're at 32 over 3 cubed. Okay, so this is equal to so the second partial of v with respect to y evaluated at the critical number is equal to, let's factor out a 32 over 9. So what remains is minus 64 minus 192, ooh, okay, over 2q, which is 8. And then let's multiply by rad 32 over 3. So that becomes 32 squared over 9. And so get some cancellations. So this guy cancels, that guy cancels. So this is equal to let's see. That's negative 256 over 256 rad 32 over 3. So I can finally write my Hessian. So now this is equal to at rad 32 over 3, rad 32 over 3 is equal to negative rad 32 over 3, which is what I got for the other guy. And so my Hessian well, again, it's the I'm going to write the determinant of the Hessian matrix. Is a rad and a minus rad 32 over 3. And then the other ones were minus a half rad 32 over 3. Oh, maybe let's do it as a matrix. So let me write these as the matrix. Rather than the determinant. Now, let's look at the determinant of, well, the very first one, the minus rad, the very first minor, the first principal minor, which is a negative rad 32 over 3. I don't really care what it is, but it's less than 0. Okay, good. So if I can get that it alternates, then I'll be happy. And so let's see if it alternates in sign, because if it alternates in sign, then we'll be here at a maximum. It'll be negative definite. So let's look at the determinant of the other principal minor, which actually is the whole matrix. Come on, oh, come on. So minus 1/2 rad 32 over 3 minus 1/2 rad 32 over 3. And rad minus rad 32 over 3. And so this will equal minus and a minus become a plus 32 over 3. Rad 32 over 3 times rad 32 over 3 minus 1/2 times 1/2 is 1/4. Rad 32 over 3 times rad 32 over 3 is 32 over 3. which is equal to 32 over 3. 1 minus a 1/4 is 3/4. Oh, it doesn't really matter what we get here, but this is equal to, well, the 3's cancel. 32 divided by 4 is 8. So this is actually equal to 8, which is greater than 0. So it alternates in sign. And so therefore, we have that V has a maximum at rad 32 over 3, comma, rad 32 over 3. But we should also note that we had originally that Z is equal to (32) minus xy x plus y. And so let's see what Z is. So Z is equal to 32 minus, well, the rad 32 over 3 times rad 32 over 3 is 32 over 3. Divided by, well, 2 of the rad 32 over 3's. And again, let's use the trick where we multiply and divide by rad 32 over 3. So this is equal to let's factor out a 1/3. Rad 32 over 3. So what remains is 96 minus 32. In the numerator, I still have 2 times 32 over 3. Well, those 3's are going to cancel. And so I get rad 32 over 3, 64 divided by, well, 2 times 32 is 64. So those cancel. So you get Z is rad 32 over 3. So therefore, we finally get that the maximum, so the dimensions of the rectangular box with maximal volume is, and these are centimeters, I believe, rad 32 over 3 by rad 32 over 3 by rad. It's a cube, rad 32 over 3. And so, just like what we would think, the maximum volume occurs